So I planned quite a bit. So let's start. Not losing much time on this. So this is just review. The last time we already talked about this. Global access means that you can get all the features for all the states. And zeta uniform action value realizability just means that for whatever deterministic memoryless policy you can think of, the action value function of this policy can be approximated in a uniform error up to zeta, this quantity. Oh, by the way, very often when you can state this as an assumption, but this is always true, right? Just you have to make zeta big. So it's kind of weird. Maybe it should be more like a definition. It would become an assumption, though, if the algorithm needs to know the value of zeta to be able to deal with this situation. Then it's sort of an assumption because now zeta is the input to the algorithm. But that's actually not the case. Well, it depends on how you are phrasing the problem, but if you're phrasing the problem such that, okay, like there is some inevitable error that's caused by zeta, and maybe that error is blown up by some factors, like square root d, and maybe something related to the horizon. But on the top of that, you don't want to suffer extra error. Okay, I think someone disagrees upstairs. And so you want to control the error on the top of this, whether you need to know zeta or not, right? Like some algorithms may need to know zeta, some algorithms do not need to know zeta. So depending on this could be an assumption or just a definition. All right. So the last time we already talked about that we're going to do some form of policy iteration where we need to evaluate the policies. And there, the first question is, how do you evaluate the policies? For this, we looked at a very simple idea, just using Monte Carlo rollouts, doing a least squares fit. So this is least squares policy evaluation with Monte Carlo rollouts. So MC, LSP, if you wish. We know how this works. You have some set of state action pairs. From that, you're rolling out with your policy. You collect the return along any of those trajectories. You average those, and then you set up a little least squares problem to learn a parameter vector. And using the parameter vector, then you can predict the action value for the policy at any given state and any action that you may encounter. And so this procedure has a reasonable behavior in terms of how well we're going to approximate the action value function of the policy. In particular, with more effort, more rollouts, longer trajectories, we can control one part of the error, which is not related to the representation error. The representation error is what it is. And it's also blown up by a factor of square d. And then the last time we talked about, okay, so if you want to make this controllable part of the error, which is like the second bit bracketed expression in equation 7 above there, how many samples you're going to need. And we saw that with the standard choice for Kiefer-Wolfowitz, where this core set of state action pairs would have d squared elements, it comes to the cube. And we're wondering, well, like, okay, could we improve this? Simple observation. Actually, if you are using slightly, like you can go with almost linear number of linear in the dimension, number of core state action pairs. So C could be chosen such that the coordinate of the C, the number of elements in C, is almost linear in D. And yet the blow-up factor would not increase by much. It would increase by a factor of 2. So you can play this game that the first factor now is increased by a factor of 2. So instead of square root D there, you have 2 times square root D. And now the D cube is becoming D squared, which is still not optimal. But you can do that. And then maybe you can do a better analysis, and then you can make that D squared to be D, and then that would be optimal. Then there is still the question of whether this 2 that blows up the approximation error is really necessary, or some magical procedure can get the best of both worlds. Just purely square root D blow up of the approximation error and linear dependence on the dimension in the sample complexity. The suspicion is that the answer is yes. All right, but someone is going to need to do that. It's not a ready-made result. Okay, so this was what we covered the last time. So now we're going to look into what happens with the policy iteration algorithm. The policy iteration algorithm works by choosing a policy, evaluating it approximately, and then taking a greedy policy with respect to the derived value function. Very abstractly, you can view this whole process as, well, the evaluation happens with or without errors. And so you can view this whole process very abstractly as like you have a policy and then you have another policy. And this policy tried to be such that it's greedy with respect to the value function of the policy we started with. So we have these two policies, pi and pi prime, and pi prime is approximately greedy with respect to the value function of pi. Okay. And the approximation error can be defined in many ways. One way of defining that is what's shown here. So if pi prime was really greedy, then it would hold that T of y pi is equal to T of pi prime v pi. But it's not, then there is an error. So it's natural to define the error as like the difference between the two things, the left-hand side and the right-hand side. And then earlier, we didn't cover because we're not doing proofs, but like it was in the lecture notes. We saw that if you have the situation that you choose a greedy policy with respect to a value function of a policy, then you're moving closer to the optimal value function by a factor of gamma. So this is expressed here. So you had the previous distance, multiply it by a factor of gamma. Gamma is smaller than 1, so the geometrically decreasing the distance, and the new distance is below that. So now if you had these errors, then there is an error term that modifies this inequality. And in this error term, you're going to have the, so one way of setting up this inequality is that you're going to have the uniform bound on the error of to what degree you are able to choose a greedy policy with respect to the previous policy times the effective horizon. This 1 over 1 minus gamma factor. And this is easy to get. And then once you have this result, then you can just use the usual proof arguments with contractions and get this result that says that if you have now a sequence of policies that satisfy these relationships, so in every iteration, there is a new policy produced. Given pi of k, you're getting pi of k plus 1, but there is an error introduced, and an error is accounted there. Then after so many iterations, I guess this relies on the rewards are in 0, 1. After so many iterations, the initial error is reduced by a factor of gamma to the power of k, which decreases in a geometric rate. Plus, you will have an irreducible error, like an error which is like only controlled by the approximation errors. So the maximum of the approximation errors along the way times this blow-up factor, which is now squared the horizon. So the square of the horizon times the worst approximation error becomes the penalty that we are paying for being lazy and not doing a good job in evaluating the policies. And yeah, so you might ask questions like, okay, is this tight? Apparently, you can show that this is tight, at least in some settings, and then maybe it waits for someone here to get a very, very clean argument that would show that this is tight. I'm pretty sure that you can show this, that this blow-up factor is tight here, that this procedure must suffer from this blow-up factor. If the errors were all 0, though, right, like there is this continuity, right? Like if the errors are all 0 or very, very small, then this term disappears, right? Like that's good. That's a sort of a continuity. So the procedure is not completely unstable or not robust, but it is somehow sensitive to these errors. And the sensitivity is expressed in terms of this blow-up factor. So this is sometimes called the sensitivity factor as well. How sensitive the procedure is for introducing errors. Then you see that, okay, like if you have any kind of contracting iteration, then this is a property that always holds. Like it didn't really matter how this operator was defined. Okay, so we see that it's not completely hopeless, but there is this blow up of the approximation error that we will need to deal with or live with. We are not dealing with it, like we are living with it. Later on, we're going to ask questions about, is this a clever design, this approximate policy iteration? It seems it's doing as if like it didn't care about these errors and it's not trying to mitigate the effect of the errors. Even if you knew that there were some errors, you can ask the question, is there anything better than this? Well, wait later to see what the answer to the question is. All right. So now, how do you apply this in our setting? In our setting, these errors are coming from approximately evaluating the action wave function. So we have some other type of errors because we're not going to get exactly the action wave function, but we're going to get an approximation to the action wave function. So there is some error. From that error, you can derive some other error for this previous thing. And then you can use this result, and then you will see that, well, the price for all of this compared to the previous setting is a factor of 2. So that's pretty easy to. It's not a big price, and this argument is relatively clean and easy. So all fine. So we can now try to put together everything, because we had this approximate way of evaluating policies where we had these error bounds and like how well we can do that and put together everything, and then we'll see to what degree we can control all the errors. Okay, so first of all, this is the whole procedure. How does it work? Well, you find this set of course state action pairs C first and this row, as in the Kiefer-Wolfowitz theorem, and then you're doing this for k iterations. That's a parameter of the algorithm that needs to be chosen in some way. You need to roll out with the policy for a certain number of steps, get the targets, at all the core states. You're only doing the rollouts there. And you're doing the rollouts with this, greedy policy with respect to the previously obtained parameter vector. So the policies are always implicitly represented in terms of that they're the greedy policies with respect to the action value function whose parameter we estimated in the previous iteration. And then once you collect all this data, you just solve this least squares problem to get the next parameter vector and then iterate and then return the parameter vector that you obtain at the end. And if someone asks like, now it's your turn to act, you don't need to do any more planning. Just take the parameter vector and then you just like to the greedy, choose the greedy action with respect to the induced linear value function, like as shown in step 4 there. So we call or I call this procedure, well, it's least squares policy iteration. That's been a name that was given to it, but there is an element of a G-optimal design here. And then there is a Monte Carlo rollout element, which is there because that's the way we are evaluating the policies. So if you took Rich's classes, then he's gonna talk a lot about TD, using TD algorithms for doing policy evaluation and trying to do that in various other ways. Here we're just ditching the whole thing with TD, because this way we can very, very cleanly control the errors, and it's not been seen that TD would have any sort of advantage over this very, very simple procedure for the setting that we are considering. So if you want another research question, that's a good research question. Like, okay, like we do have a lot of people who are fans of TD. Do they know something that we don't, or like, yeah, like should we also be very excited about TD? That's really the question. Maybe there could be multiple reasons to be excited about TD. It's incremental as opposed to least squares. It doesn't have to collect the data. It doesn't it's kind of doing everything online, incremental fashion. At the same time, it does have these parameters. So here also, we do have some parameters, but they're super simple to tune, right? So choosing the number of iterations and choosing, the more iterations you're going to have, the better it's going to be. Choosing age, the larger the age is, this truncation, the better it is going to be. And if you're shooting for a certain accuracy, then you will know how to choose these things. By the way, yeah, so there was this thought that occurred to me that with this error bounds and already this error bound for approximate policy iteration, I didn't mention this. But the geometric view of this is that, well, policy space doesn't really matter. What matters is where you are in the value function space. And so, I don't know, like here is the value function space. And we know that the set of value functions doesn't look like this. It kind of looks like this. Here is V star. So here are the coordinates for all the state action pairs. So this is the first state action pair, and this is the last state action pair. And you have some value, and we know that the value functions they're forming a convex set, and V star sits in the corner. And whenever you choose a policy, you're going to have some value function. So you will zigzag here and hopefully approach V star. Now, people are talking a lot about whether you're approaching V star or not approaching V star. So if you have these irreducible errors, it's not really expected that you should be able to reach V star. Like, why would you be able to do that? Like, it's completely unreasonable to expect that. So it's what is expected though is that you get in a small vicinity of V star, of some radius, okay? And the smaller that radius is, the better things are gonna be. And the other thing that's expected is that you get there fast. So you're not like going sideways all the time. Do we expect monotonic improvement? Well, I don't really care about that. As long as I get very quickly in a small enough vicinity of V star, I'm good. And then once I'm in the vicinity of V star, we can zoom on this. So it's going to be, this is how it looks like. Policy iteration is gonna do like nothing. It's gonna, in general, chatter, go around. Like it's not going to converge. Like why would it converge? Like there are these uncontrolled errors. It doesn't need to converge. And it's not expected that it should converge. So people are talking a lot about that. Oh, this chattering, jittering, we should reduce it. I don't know. Like, why do you expect to be able to do that? I don't. I don't think that that's too reasonable. It would be very expensive to do that, I would say. So if you, here what we are trying to do is that we try to avoid any procedure that depends on how many states you have or something like that in the word. Like you're compressing everything down to a feature representation. You have a compressed and approximate view of the word. With an approximate view of the word, you can't get precise answers. So just live with that, right? But we can try to reduce this radius. So here, this is the radius, right? This is your radius. And so here, the radius depends on two things: how big the approximation errors are, and the other is this blow-up factor. The blow-up factor, if anything, should make us pause for a moment and wonder about whether, well, that should be there or not. Can we do something about it? The approximation errors, well, choose better features if you can. Okay, people are talking about learning features, fine. You can try to do that, but expecting a procedure to be able to learn features, for example, to reduce this radius to nothing, like that would definitely conflict with some lower bound that would say that, well, okay, then that procedure needs to see all the state action pairs, and like that's not going to be efficient. So just because we are saying things like, oh, we're going to learn the features, that's going to be much more powerful. Well, it is to some degree more powerful because you have more representation power. Maybe you have more troubles as well because you can't use just linear algebra, so you have to deal with nonlinearities and whatnot. But it's not quite a magic bullet. It can be. Anyways, we have seen a bunch of these lower bounds, right? Like without extra information, like all the algorithms have to see all the state action pairs. Like don't forget that. Okay. All right, rant over. This is the procedure. It's nice. You like the meaning of the parameters is super intuitive. More iterations, you can expect it to improve, but it's gonna chatter eventually, right? Like that's fine, but it should improve. If you throw at it better features, it should improve. That's also good. And if the truncation is happens later, then it's also going to be improved. So everything is nice and under control, and lo and behold, you can prove this result where you can show that for any choice of k, m, and h, the policy that we obtain after k iterations of this procedure is gonna produce a data suboptimal or data optimal policy such that data is at most of this size. All right, so here we have an approximation error with an h² blow-up factor and the square root d. We have an iteration error which goes to 0, geometrically fast, super easy to control. And we have this policy evaluation error, which we can control both by making h large, the truncation target, and the number of rollouts to be larger. So everything is under control. You can control all the terms if you wish. So it's all very nice. You can ask the question, could it be better? That's a valid question. And if you look at the total computation cost and the sample complexity, and you just accept that the error is going to take up this form, that is the blow up from the approximation error, and then there is some extra error that you're trying to control. This is the error that's under your control. Then the cost of controlling that is going to be polynomial in the horizon, in the dimension, the number of actions, the inverse of this error, don't need to square that, and log 1/0 or whatever, which is like this inequality holds with probability 1 minus 0. Okay. So that's the result that you can have for this algorithm. Yeah, I think it's quite reasonable for such a simple algorithm. But that's why I like this algorithm. It's super intuitive. It's super simple. The simplest thing. This should be the baseline, right? Like we need to compete with this. So now notice that we started this whole function approximation business by saying that, well, okay, we don't want to look at all the state action pairs. Therefore, maybe we should do online planning because then we can get away without looking at all the states, maybe at an exponential cost in the horizon, but okay, this lookup tree. So that was like online planning. But then we didn't like the fact that things blow up exponentially with the horizon. And then we said, okay, let's add function approximation. Then you can still do online planning, or you can do offline planning. And this is what we're doing here, right? So here, this procedure, what it does is that it talks to the simulator for a while, and then it stops talking to it, produces a policy, summarizes all the data into a single parameter vector, which is returned. And then from that point on, it doesn't need a simulator if it is deployed, right? You can deploy the policy that is learned. You just need this parameter vector. So I call this, it was called in the lecture notes global planning, but I think it's better to call it offline planning because you're doing this before you're interacting with the system. You're not doing it online. Okay. And the other thing to notice is that, well, okay, this is global access as opposed to local access simulator. It still required this G-optima design, which for what we know could be intractable. By the way, if you talk to a numerical analyst, they're going to have very specific ideas about how to use basis, how to choose basis functions for solving a certain numerical analysis problems. And why I'm talking about this, well, our problem in a way is a numerical analysis problem because we just have these numbers sitting around. We want a good policy that does something, and like it's just about numbers and then computation. Numerical analysis, it's like computation over the reals we discussed. And they do have these ideas about the basis functions. And because they have specific ideas about the basis functions, they will have specific ideas about this optimal designs as well. It's not like that this optimal design is always intractable. If you are choosing deliberately the basis functions in a certain way, optimal design may be free. Maybe you just know where to query. to get these nearly orthogonal vectors that the optimal design requires. Anyways, I just wanted to mention that maybe it's not all that bad always, but if you want to be very agnostic to the features, like you're not the one choosing the features, therefore you will have difficulty choosing this core set of state action pairs. And there is a question of, okay, like what do we do with this algorithm? This algorithm is not that practical then, because we don't know in general how to calculate this optimal design. All right. So we want to get away without global access. We want to go back to local access, no need for optimal design. And this was done recently together with my dear colleagues at DeepMind, Long-Ying, Bodo, Yassin, Nevena. And we call the resulting algorithm confident Monte Carlo LSPI. It's a simple modification of the previous algorithm. And I described it the last time, but now we do have a little bit more details about this. So here's the full algorithm. And the whole thing revolves around this core set, which we don't have at the beginning. So we're going to need to initialize it in some way. The whole idea of the whole procedure is going to be that given a core set, if you encounter some state action pair, you can measure how uncertain you should be about any function that you are estimating using those features. So if you trust your features, you know the uncertainty level that you can expect. So this algorithm is going to have this tau tolerance level that is the level of uncertainty that is able to tolerate, and you need to choose the tau in some way to run the algorithm. So that becomes another hyperparameter. And so what the algorithm does is that it's just using the usual design matrix. There is a small regularization added to that, and that's actually a good thing. So lambda is, okay, we have another hyperparameter lambda. But we're not going to do any, so don't freak out. We're not going to do a grid search over the hyperparameters. We're going to choose them in a principal manner. Okay, so this a little bit modified design matrix so that we are avoiding the design matrix being singular. And then we look at this predicted uncertainty level. And if for a state action pair, the predicted uncertainty level is high, then we expand the core set. So we also have an initial state. So initially we do this at the initial state. And we want all the actions, like we want to be confident about all the actions. So we just iterate over all the actions and then check to see whether we can be confident already. And if not, then we're just expanding the core set. And here in the core set, we're collecting some data in addition to just like what the state action pair is and what the corresponding feature vector is. There will be some target, like that will be like the result of the rollout. And the beginning, there is no rollout there. So that we are initializing it with none. It's just like some data structures thing. So it's not important from the perspective of the algorithm. Okay, so once this is over, we do have a core set which is non-empty. Okay, now we can start with our policy iteration. So we're gonna have the same loop over k loops of policy iteration. And what we were doing before is that we were just solving a least squares problem. We set up a least squares problem, and then we solve the least squares problem, and then we get the next weight. So here the weights are W, not theta, but that's the only difference. So given the previous weights, we're going to do all these rollouts, and we're going to get something out of this. Either the procedure is going to say they're all good, then then the result is a valid result. So we are doing this rollout for every element of the core set. So we are doing this rollout, and we get back a status and a result. And if the status is done, that means that like nothing special happened. Like we're gonna be confident that the result that we get is a good target. So if that is the case, we just store this. Like, okay, this is our target at this core state action pair at Z. Okay, so this ZQ arrow result means that we are storing that in the set. Otherwise, we detected that we can't be confident about this evaluation of the policy in this rollout. In which case, it is because we got surprised. We have seen some state action pair that surprised us. Then we're going to expand the core set. So the result in this case is going to be a tuple of this form. Okay. And when this happens, then we just abort and restart. So we go to this start line, just break out of this loop, and we restart the whole procedure. You can refine the analysis so that you don't really have to do this. But you just want to make sure that after you discovered some state action pair, then you iterate for long enough, because maybe all the previous results were garbage. Okay, so you wouldn't need to necessarily completely restart the procedure. You can also try to detect when you should be stopping, and then like you can do a bunch of these optimizations, but you know, simplicity is also nice. So here we just abort. And so we collect all this data, and once the data is collected, then we just solve the corresponding least squares problem. So this notation just like, okay, a little bit complicated looking, but it's just solving the least squares problem with the collected data and adding a little regularization to it. And so that's the whole procedure. So what is at the end? This confident rollout procedure, what is it doing? Well, it's not doing anything really special. It has this, so the input is number of rollouts, length of rollout, policy parameter, discount, initial state, initial action, and the feature matrix. And so there is the initial state. So that's not really initial state for the problem, but initial state from where the rollout should be happening. So that was here, this Z. So here, when you have the Z has an S component, an action component, because it has this row, that's a state, that's an action. There's a phi component, I guess, and it has a Q component that's like the estimate of the action value, the return estimate. So there is this initial state. And so we reset the simulator to this initial state, and then we start to run the simulator from the initial state. And here, it's kind of like this. We're going to build a trajectory, but along the trajectory, at any step, we're going to try all the different actions. So it's, what does this resemble? I don't know. Some beautiful, I don't know, weed, or it's a long branch and like very, very short little branches. So those are all different actions. And we're gonna check. So we came so far. It is a state. So we're trying all the different actions, and we see whether the corresponding feature vector is something that would surprise us. So if there is an action such that we are surprised at this tau level, then the status is not going to be done. It's going to be that, oh no, like we are surprised. We got caught off guard. And we're going to return the corresponding state and the action and the feature vector to expand the core set. So whenever you're surprised, you just like remember that, oh, I got surprised here. So I need to add this to my central memory of like what I need to pay attention to. So you're gradually building this core set. So it's very, very simple. It's basically the same algorithm as before, except that when you're running these trajectories, you're constantly checking all the actions. For building a rollout, we didn't have to do this fanning out with the actions. The cost is still linear in the length of the trajectory, but it's multiplied with the cost is multiplied with the number of actions. So it's like the rollout is 8 times more expensive. So if you have a large number of actions, then this could be pretty expensive. But okay, we're just shooting for simple case when the number of actions is not so big that this is infeasible. So then this is almost as efficient as the previous one. So why do we do this checking? It's because we are preparing for switching to a new policy. We're gonna rely on maybe when you're running this policy, then you want to do this look ahead using your action value estimates. And you want to check whether any of the actions is better at a state that you're going to visit sometime in the future when maybe you're deploying the policy. And you want to make sure that you're not surprised if you would be checking this. So your uncertainty is under control to the degree that you're pretty confident that the greedy action is not misleading you. Okay. So so this is why these extra steps are there. And other than this, it's just the usual thing. Okay. This is the algorithm. Do you have any questions for this? Because this was not in the lecture notes. Yeah, Vlad.
Yeah, so this way of building the core set, is this similar to how like they would do it in G-optimal design and like with the offline case? Like, was that inspired at all by that? It seems kind of like a upper confidence bound type of idea almost.
I think you have kind of 2 parts to your question. One was alluding to that people are doing optimal designs in some incremental fashion. Maybe they do. I don't know if you don't have this extra structure that we have here, that we're actually running policies on a simulator to generate new data. Then if you didn't have this structure, like you just have supervised learning or something like that, I don't know how you would do this, right? Maybe in supervised learning, what you could do is to maybe you have a way of sampling the data or something like that, and then you could do G-optimal design in an incremental fashion this way. I'm pretty sure that people have explored this there, but I'm not aware of any specific papers doing this. But it very well may be that we are inspired by something that I've seen and don't remember anymore. But yeah, I don't know of any papers doing this. But the second part to the question, if you want some confidence bounds for the value estimates, we didn't talk about this, but it's kind of obvious from the calculations that we were doing. You can have those, and the width of the confidence interval is going to be exactly the square root of this quantity that is being calculated here. It's proportional to that. Okay, so this is this quantity. This is the square root of that is the width of the confidence interval. And if you put it this way, then you can see the whole thing as just making sure that this confidence intervals are not too big. And in upper confidence bound designs, you would go always with the upper, like the value which gets a bonus based on the uncertainty. That would be something different. But it's definitely, like using the same formulas and same ideas. Here, we're not sure whether if you just like switch to this upper confidence design, for example, that the resulting procedure would be a sound procedure and you would be able to prove the same result for it as what I'm going to show on the next slide. So that's an open problem, as far as I know. But maybe it's not to learn. Yeah, Jimin.
Yeah, I see that here we check all the actions of the states we encounter in the rollout. Why we don't have to like control the unconfidence over some states that we don't encounter in the rollout. I know lookup
Right.
states would be expensive and it would be
Yeah.
the size of
Sure.
state space.
But why is
But
it
how?
to
Yeah.
just do this? Well, it's a complicated story. It's not trivial to show that this is sufficient. Maybe at a very high level and intuitively, you could say that at the end of the day, you're going to use this policy. And if there is a state that is not accessible by this policy with high enough probability, then the fact that you're uncertain at that state is not going to matter much. So somehow you need
So
control for this.
I see. So the probability of going to those kind of state like is low, is controlled.
Yeah, altogether it has to be, because if it was that with high probability you would encounter a state where you would be surprised with the chosen policy, then there you would just go with garbage, right? Like there, the action value function estimate is not precise enough for you to choose the next action. So it has to be the case that that the probability of encountering state action pairs where you could be surprised must be low. The proof doesn't go that way. The proof somehow uses some simulation argument that avoids this, because it would be very complicated to reason about this.
Okay.
In a way, that's kind of the innovation of this paper, of reasoning explicitly about this.
Okay. Thank you.
Yeah, you're welcome. All right, any other questions?
One more. So when we in the G-optimal design version, we had this like assumption that we could get like on the order of d squared number of state actions that we should query the features of. And we said that that can happen like some of the time. Like you can have it such that it's not even possible to get, like it's not sufficient to look at only d squared features, right?
What? Well, okay, so if you're sequentially searching the features, then if you only look at these squared features in an arbitrary order, it will be
Yeah.
bad, right? Like you may need to sequentially search the whole set of features.
Yeah, and then G-optimal design guaranteed that we only need to look at d squared of them, that were chosen in like a very special way
Right.
from this matrix. And I think we also said that this can only occur for some feature maps,
Right.
where some other, like in general, you could have a feature map that's not
Less.
sufficient.
No,
And
it's the other way around. Like this squared may be overkill.
I see. So there's always for
The
any
that
feature
is
map,
an
right?
absolute.
For
That's
any
the
feature map,
saying.
right? So for any feature map, we can subselect like d squared
Right.
states and actions and
Right.
only look at those features. And that's in general for any feature map.
Yeah, that was the generality of the key
Right.
for.
Okay. Yeah, that's fine.
And I thought that you're gonna ask of like at the end, how does the size of the core set that is collected here compare to the size of the core set that we would get from Kiefer-Wolfowitz? We do have an explicit bound on it. And it's going to depend on various parameters, and the dependence on d, I think it's d squared still, or maybe slightly worse. The dependence on the dimension of this algorithm is not really that great. So one immediate follow-up is to improve like the sample complexity of this algorithm. Okay, so let's go to the next slide. It's polynomial in everything. It's all fine, but it's pretty high. So this algorithm is highly suspect that it's not as efficient as it could be. But still, for this setting, local access, offline planning, I think this is the first algorithm that actually gets this result with a computationally efficient procedure without extra assumptions. Like the previous algorithm was like, oh, give me a core set. Well, okay, like I can't. So yeah. So this is the result that we can show, and deliberately I chose not to show the horrible polynomial that is going to be h to the big number, d to the big number, and so on and so forth. So one of the things that you may notice in this result, and I think the previous one as well, I guess this A dependence, like A appears everywhere in a polynomial fashion. On the one hand, we shouldn't be surprised because, I mean, in policy improvement, you need to search through the actions. So in terms of just the computation cost, it's already there. But in terms of, like everything else, if you only do regression, the coordinate of the domain of the regression, so it's here, it's the state action pairs, number of state action pairs, and that the number of actions is also there. It's not there. So in terms of the sample complexity, just thinking about regression, like it's not justified to have an explicit dependence on the number of actions. Yet in this procedure, it's very clear it's gonna happen, right? Because we are doing these little fan outs. I don't know, how do you call this? How do you call a branch which just have like very, very short sub branches?
Which call it tree backup, something like that. But
Yeah.
this can be called tree track. I don't know.
Okay, yeah, I think I've heard it. All right, cool. So that's that. All right. So questions, can we do better? In terms of the this is related to the approximation error. So if that is the an irreducible approximation error, then if your target accuracy is too small compared to square root d times that error, then you can expect your sample complexity to be exponential, to be large. In particular, it's exponentially large in terms of the ratio of the approximation error times the square root d blowout factor divided by your target accuracy. So if you want to go below this radius that I was talking about, the square root d epsilon, then the algorithm suddenly need to work very hard. Well, or suddenly, or I don't know, like it's gradual around though, right? Like it's not like suddenly this blows up, but like if, delta is in the range of epsilon, then this would be exponentially large already in the dimension, which would be considered big for anything reasonable. So Yeah, this goes back to this, like, but can we learn the features, or like, no. I mean, no procedure is gonna solve miracles. This is a needle in a haystack argument again. It's like, features help you to some degree. The square root d is what's interesting here. That the approximation error, you can multiply it with square root d, and if you're demanding a precision below this blown up approximation error, then you can be in trouble. If you accept the square root d, it's fine. It's kind of a sad story, because the approximation error already is cringy. It's probably not that small. So you want to scale with it just like that, but you can't really go below it, or like not even match it. It's like you have to pay a price of square root d if you, strictly speaking, want to pay or guarantee polynomial sample complexity. By the way, this has very little to do with multi-stage planning. This already happens in kind of a bandit problem where you just have actions, you have one state, many actions, and you want to choose the best action, and there are features that are helping you to choose the best action. So because of the features, you don't need to choose all the actions to learn about the values of all the other actions. So you might be hoping that if the features are good enough to represent the reward up to an epsilon accuracy, then you get away with polynomial in D samples, and you will be able to choose an action which is epsilon suboptimal. And this happens to be false. You can only choose an action which is square root D times epsilon optimal. You can't go below that. Why? It's because the data that you're collecting, it's for this very restricted view of all the actions. There's many actions. You only collected data for very few actions. You want to extrapolate to the other actions, but in a d-dimensional space, you can have actions which are nearly orthogonal to each other, and there are exponentially many of them. And the feature vectors are nearly orthogonal. And if the feature vectors are nearly orthogonal to each other, then you can't transport the information from where you collected the data, right? So this is the lower bound, and it's kind of devastating news, but well, you just can't do any better than this. And so this was happening when you had many actions. And now you might ask the question about what happens if you don't have many actions, because like very often in MDP setting, we look at the case when you only have few actions, or you might have the idea of like, if you add many actions, maybe I increase the horizon because I'm gonna break up, like this binary encoding of the actions. Like I choose the bits of the actions one by one, the state is not moved. So in the log2 number of actions, extra steps is introduced, and I blow up the horizon by that factor, and then I still solve the same problem. And no, that's the only thing that happened, and I have two actions. So would this work? Well, this wouldn't work either. So first of all, the features wouldn't work for the intermediate stage. It's like you can't really invent the features. Like, okay, so the reason this doesn't work is because we have this lower bound result here. Okay. But this tells us is that like you can try to do this. Let's break up the actions into these smaller parts, but you will not be able to invent features. Because if you were, then you would be able to break this lower bound. But there is this lower bound, so you can't. So in food generator, you can't. Like if you have some extra knowledge about features and whatnot, the word, and like for some reason, you can do this. Sure, like special cases, go with it. But there's this idea of let's just like reduce the number of actions to a small number by introducing multiple steps in the word. It just like doesn't buy you the part that you expect it to buy. It doesn't make the problem simpler in any ways. And it would only make problems simpler if you could somehow induce the features so that like for the intermediate stages, you can also use the features and then you can generalize, and like you don't have to then look at the full tree. Like we expanded, notice any action was expanded into a small tree. That you don't have to serve the full tree. You could use the features inside that little tree, but this lower one just tells you that, well, this is not going to happen. So, okay, so one more thing to give up. It was a great idea, but it's just not going to work. Right? Isn't it great? Okay. We're done. Questions? So, Axon, do you want to ask your question?
Yeah, so I mean, this lower bound came about basically out of making some nearly orthogonal vectors on the unit sphere. And well, I thought like when people want to talk about PCA, they say that, well, you have this data that's three-dimensional, but really it's mostly like in a very small subspace, linear subspace. And like if you pick just a few principal components, then that explains your data almost fully. So what I was thinking was that, okay, well, if like in many of the problems we will encounter, this is actually this like, I don't know, it's really what I should call it, an intrinsic dimensionality, or the actual dimensionality of this linear subspace is much smaller than the, let's say, of log of d, order of log of d. And then that means that like these like vectors are going to be restricted within that small subspace. And so the lower bound we would have eventually would not be as bad as just using d itself as the dimensionality. So this is what I was thinking. And I mean, like, there is this like disclaimer that like PCA is usually what people use for supervised learning, and I thought maybe like the problems we'll see in reinforcement learning aren't like that much like the supervised learning problems, and maybe we don't have that in the first place. So yeah, basically, I just want to say if this is a reasonable assumption to make, just ensure that like in real world problems, sometimes we, like in some interesting cases, we won't have this problem.
Yeah. I mean, the result is worst case, right? This lower bound. So if you have some extra conditions like what you are talking about here, then definitely the lower bound can be avoided. And so one part of the question is maybe to make it a very crisp question. If all the action feature vectors would lie in an r-dimensional space rather than a d-dimensional space, then would anything change? And yes, then you would just need to replace the d with an r. And in the upper bound as well, you can do this, by the way. So the other part of the question is maybe, which was not asked, is that people when introducing PC and whatnot, they have all kind of elaborate procedures to somehow exploit this low dimensional setting. And then the question is, do you really need to do that, or just usual least squares is gonna work?
Well, I mean, yeah. So, I mean, I wasn't really talking about like
You're not talking about that. It's just like I'm really associating. But I think that's a logical follow-up question, which maybe
yes.
we discussed here. And that the answer is that, like, it seems to me that if you're just regularizing least squares, then you don't have to do anything else, and you will get this dependence on the lower, like the actual dimensionality of the feature space. Automatically, the procedure kind of, like, you can have an universal regularizer. Okay, the hyperparameters, going back to hyper, like, we never want to have some hyperparameters such that they need to be chosen based on the knowledge of the problem you're trying to solve. Oh, that's cheating. But it turns out that you don't have to do that. You can have a universal choice for the regularizer such that you're automatically adapting to the dimensionality of the subspace that the features live in. And you don't have to pre-process the data, or you don't have to estimate this subspace to take advantage of it. So that's a nice property of regularized least squares.
Yeah.
There was some other part of your question. So, or did I answer everything?
Oh, as in, like, you are asking me to.
Yeah. Okay. So that was the part of the question, whether it's a reasonable assumption or not.
Yes, like in a reinforcement learning problem as opposed to supervised learning. Yeah.
I think I don't know whether I like these questions, because
Subjective.
it is like, how do you decide? Like, yeah, there is no objective measure of, like, well, how is reality? Like, is reality such that these low dimensional things do happen or not?
Right.
I mean, some people do say that they happen. I find it interesting when something like this happens, and you can ask whether you can design an algorithm which adapts to this specific setting. And I think that question is very reasonable to ask, regardless of whether it's supervised learning or reinforcement learning. So it's very relevant in reinforcement learning as well. Oh, one more part of this is that, again, these results are worst case, and we already talked about state aggregation. In state aggregation, none of this happens. This D is not there.
Yes, yes.
But it's a full dimensional space. So it's for yet another reason the blow up doesn't happen. So yeah, so the picture is much richer than just like what is conveyed by a worst case result, right? Like a worst case, yeah, like square root D is unavoidable. It seems pretty bad, but maybe there is a much richer picture there. Anyways, good.
Yes. Okay. Thanks.
All right, Jiamin.
Yeah, the slide is not okay. So in the bound of the LSPI, and that this term that is not controlled by choosing like H or K or AND. So I was wondering, why shouldn't we worry about the size of the board, or can we control the size of the board? And more specifically, what is the relationship between the dimension of the feature D and the epsilon? Yeah.
Okay.
So intuitively, I feel like if we want to reduce epsilon, I feel like in some problem, maybe we need to like increase the dimensions of the feature space.
Right. And then, okay, what is, like, one factor is decreased, the other is increased. It leaves you with this uneasy feeling that maybe you're not doing anything. Right?
Yeah. Yeah, yeah, because they appear in the bonds in this way that
Right.
feel
So
like
it's
we
not
have
only enough to use feature vectors of a larger dimension, but you should do it in such a way that the price that you're paying for blowing up the approximation error, because you need to extrapolate, and that was not a reinforcement learning thing, that was just supervised learning thing.
yeah, so
Is not larger than the gain that you had by introducing more features. So features, if you need to control extrapolation errors, are not for free for any procedure. So I don't know. Yeah, I think it's okay. So a very high level. First reaction would be, yes, of course you should worry about it. But second reaction, of course you shouldn't be worried about it. You should be a stoic. You should be worried about the things that you can control. So if you're designing algorithms, then like worry about like what's under your control, and don't worry about the things that you're not controlling. But someone needs to control these other terms as well. And so you didn't talk about it, but there is this.
yeah, I
This
would like to ask.
but
Yeah,
actually, it's part of the question, right? Like it's at the end. Like if gamma gets very close to 1, that factor also blows up. So should we be worried? Absolutely, we should be worried about it. And that's a negative question. So maybe we can control some of that, and then okay, revealing secrets. So later on, we're gonna see algorithms where this is replaced with 1/1 minus gamma. So there are better procedures in this respect. The square root d, worst case, it's gotta be there. The 1/1 minus gamma squared, no, doesn't have to be there. And you
yeah,
should be worried about it. Now, and this could overwhelm the whole procedure, right? Like, I think that when people are running reinforcement learning algorithms, these algorithms mostly resemble the algorithm that we are discussing here. Variations of policy iteration, variations of value iteration, with least square fitting, maybe throwing a neural network. There is not much difference. They're gonna show this picture that I drew earlier, where they're making progress and then eventually they're zigzagging around. The size of the neighborhood where they're zigzagging around, that is this controlled by these things, right? So the square root d, the h squared, and whatnot. But now the h squared is interesting because that's actually controlled, like that's an algorithmic aspect to the problem. The others, maybe not so much. But anyway, so long story short, what I wanted to call to your attention is that if you look at plots that people make for individual runs of reinforcement learning, they often look like this. The performance improves, and then it's like, okay, okay, so that's an algorithmic problem. I think then they have an unstable algorithm. That shouldn't happen. It can go up, and then like it should stay up, and then it can jitter there. Like I'm totally fine with that. Then like we run it long enough, we select the best in retrospect, measuring back to the quality of all the policies. That's easy to do. So that's fine. But there's like this collapse. The collapse is what we need to take off with better algorithm design. So those are signs of like poor algorithmic choices. When you have the collapse, this other one, this jittering, I think that like when you are dealing with this approximate setting, then you can only do so much about that. Yeah. Okay. So having said that, yeah, of course you should reduce all the error terms that you can.
okay.
Okay. All right. We don't have anything else. Good. We are done on time. First time it happens in the semester. So do you have some stories to tell me or some more questions?
I have another question about the first lower bound. I haven't thought about this that much, but I was just thinking about the so the result. So we start with like this delta epsilon planner that's our goal that we want to obtain, right? And the lower bound goes by like constructing basically this bandit problem that has a actions, which we're going to choose a large enough. And one of these actions has a reward which is larger than the delta. So we need to like find that action. Otherwise, if it's lower than delta, then I mean, we're fine because our goal is to make a delta optimal planner. And then all the other rewards are 0. And then in a sense, and then we need to choose features, which we have the option to do, such that those features are sufficient to be epsilon, like within epsilon of approximating the value of that MDP. And we say with the Johnson-Lindishaus lemma, right, that we can do this with D features, where D is really a logarithm of the size of A, or A is exponential in D. And it seems like what that tells us is that the JL lemma tells us that we can choose sufficiently little features to still achieve this epsilon, such that yeah, like basically our features can be almost like it sounds like they can almost be good enough to only need a logarithm of the size of actions to be like epsilon close and approximating. And so because our features are chosen to be this good in a sense, we kind of suffer this inherent problem that we're always going to have to search through all these actions, right? Like that is unquestionable regardless of your features.
Yeah.
And so can't we just not even like more naively like choose a state aggregation for the features, like set D to 1, and then your features are just 1 for that one action that gives a reward and 0 everywhere else, and then you still will achieve that like epsilon realizability assumption, right?
Didn't you just blow up the dimensionality to match the so the way this works is like the mechanism of the proof was like what you described, but the result, the way it is set up, is that for any D and epsilon and delta, this result holds.
Yeah.
Then you choose the action space to be just of the right side, rather than thinking the other way around. Of course, you can think the other way around as well.
Yeah.
But like with the choice that you're making, I think you're tying D and coordinate to the actions together, and then you wouldn't get this result that says that for any D whatsoever. So in particular for state aggregation, are you even aggregating together any actions, or you were not even aggregating together any actions? You were just choosing orthogonal vectors. Then I had the feeling that that's what you're suggesting.
I was suggesting that there's 2 aggregations. There's all the actions that give you 0 reward as 1, or they output a feature value of like, let's say 0. And then the one action that gives you a reward.
That's lacking something. So in the lower bound construction, you choose the feature vectors in a special way such that you have as many as the actions, different bandit instances, each having the needle in a haystack property.
Mm-hmm.
With feature vector that you're describing, you don't have this. Right? The features are giving away the identity of the optimal action because you're aggregating together all the suboptimal actions. So I just read the features and I don't even have to query anything and I'm done. So I think that was an excellent question because it points to this point of the construction that you have to choose the feature vectors such that you can support this large diversity of different problems. So that create the needle in a haystack.
Right. So because those features are you have those same features that we constructed across all
No matter-
cardinality of A or K MDPs, where each
Right.
of them have this different location of a need, and then yeah,
Right.
that's all. Okay, yeah, that solves that because I was like, this seems very odd that you can just make this even more
Yeah.
ridiculous lower
Yeah.
bound.
Oh, it's good. It's good. Yeah. I like it.
Yeah, thank you.
Okay. All right. Okay. Thank you, everyone. Talk to you next week.